Well, we finally know why the world's largest supercomputer landed in Memphis. XAI.
For more than a decade, the car industry operated on a single unspoken agreement. Electric vehicles could be fast, or they could be efficient, but never both. Every engineer in Detroit, Wolfsburg, and Tokyo treated that trade-off as a law of physics, something you designed around instead of something you could actually break. Then, almost quietly, without a press conference built around it, Tesla shipped a part that ignored the agreement entirely. It wasn't a new battery chemistry. It wasn't a flashy new body style. It was a motor. And buried inside that motor was a decision that, years later, still has rival engineers taking components apart on a workbench, trying to figure out how Tesla pulled it off. Rewind to the early 2020s, and the skepticism toward Tesla was not irrational. This was a company that had, more than once, promised the world and delivered a fraction of it. Production targets slipped. Delivery timelines stretched. And sitting across the table were companies that had been building cars successfully, profitably, at colossal scale for the better part of a century. Ford had assembly lines optimized down to the second. Volkswagen commanded a global supply chain most nations would envy. Toyota had turned manufacturing efficiency into something close to a religion. Against that kind of institutional weight, a company that had only recently figured out how to make cars without losing money on every unit looked, to a lot of very smart analysts, like it was living on borrowed time. The electric vehicle boom only sharpened that skepticism. As traditional automakers rolled out their own battery-powered lineups, the early novelty that had once made Tesla untouchable started to fade. A Tesla badge alone no longer guaranteed a sale. Rivals were building electric cars that looked good, drove well, and cost less. The gap that Tesla had opened in the mid-2010s appeared, to plenty of observers, to be closing. And there was real substance behind that closing gap. General Motors had spent years developing a dedicated electric vehicle platform and was rolling it out across multiple brands. Volkswagen, still working to rebuild trust after its diesel emission scandal, had committed staggering sums to electrification. Hyundai and Kia were producing vehicles that consistently ranked near the top of independent reviews. On a spreadsheet, the math looked simple. Whoever could out-manufacture and outspend the competition would eventually win, and Tesla did not have the deepest pockets in the fight. What that spreadsheet math missed was a part sitting inside a motor that almost nobody outside a small circle of powertrain engineers had thought seriously about. Every electric motor works by spinning a rotor at extremely high speed to generate power. The faster that rotor spins, the more force it produces, but also the more centrifugal stress it has to survive. Push a conventional metal rotor too far, and it doesn't just wear out. It deforms, then it fails, sometimes catastrophically. That physical ceiling is precisely why most electric motors in production vehicles are engineered to stay well below their theoretical performance limits. Manufacturers weren't being conservative out of caution alone. They were respecting a hard structural boundary. Tesla's engineers approached that boundary differently. Instead of accepting the limit, they wrapped the rotor in a carbon fiber sleeve, a material prized in aerospace and motorsport for offering enormous tensile strength at a fraction of the weight of metal. That sleeve acts like a containment vessel, holding the rotor together under stress levels that would tear a conventional design apart. With that containment in place, Tesla could push its motor to spin at speeds far beyond what the rest of the industry considered usable in a production car, reportedly north of 20,000 revolutions per minute, a figure closer to what you'd expect from a jet turbine than a family sedan. The immediate benefit is obvious. More speed, more power, blistering acceleration. But the second-order effects are where things get genuinely interesting. A motor that can spin faster can also be made smaller and lighter while producing the same output, because power output is a function of both torque and rotational speed. Shrinking the motor frees up physical space and cuts material costs. And because the carbon-wrapped design runs with tighter tolerances and less wasted energy, it also runs cooler, which means the car needs less cooling hardware wrapped around it. Fewer pumps, smaller radiators, less plumbing, less weight. Every one of those savings compounds into the next, and the net result is a motor that is simultaneously faster, lighter, cheaper to build, and more efficient than what came before it. That is the exact combination the industry had spent years insisting was impossible. Here's the part that should genuinely unsettle any competitor studying Tesla's playbook. The carbon-sleeved rotor is not some closely guarded secret formula. Carbon fiber rotor wraps already existed in aerospace and racing applications before Tesla ever used one in a road car. Any engineering team with enough budget could, in theory, read the same research papers, source the same carbon fiber, and build a working prototype in a lab. The problem isn't the concept. It's the execution at scale. Carbon fiber destined for this kind of application arrives as a pre-impregnated tape that has to be wound around the rotor under precise, unwavering tension. Wind it too loosely, and the rotor flexes and fails once it's under real stress. Wind it too tightly, and the fibers themselves crack before the part ever leaves the factory. Then comes curing, a heat and pressure process that has to hit an exact window, because miss the temperature or the timing and the entire component turns into scrap. After all of that, each finished rotor still has to be balanced to a tolerance most manufacturing plants have never had to work with, because an imbalance that would be completely invisible at highway speeds becomes a violent, self-destructive vibration once you're spinning at tens of thousands of revolutions per minute. None of that is a one-time engineering puzzle. It's a manufacturing discipline that has to be repeated correctly, thousands of times a day, without the scrap rate eating. The profit margin alive. That is not something you download from a white paper. It's something you learn the hard way, one ruined rotor at a time, across years of production. And that kind of institutional knowledge doesn't transfer between companies the way a patent or a blueprint might. Analysts who study these components for a living have suggested that catching up to Tesla's manufacturing maturity on this single part alone could take rival automakers the better part of a decade. Not because the idea is hidden, but because the execution is brutally hard to replicate profitably. The Model S Plaid, the car that first showed off this motor to the public, was never meant to be the endgame. It was a proof of concept wrapped in a six-figure luxury sedan, a demonstration that the trade-off between speed and efficiency wasn't a law of nature after all. The real target was always further down the product line, in the mass-market vehicles that make up the bulk of Tesla sales. At its 2023 investor presentation, Tesla laid out a startlingly specific ambition: engineer a next-generation drive unit, motor, gearbox, and power electronics combined, that costs roughly $1,000 to produce. For context, some competitors reportedly spend several times that figure to achieve comparable performance. On a single vehicle, that gap might look like a rounding error. Multiplied across 1 million cars a year, it becomes a multi-billion-dollar cushion, one that funds new product development, absorbs price wars, and lets Tesla cut prices in a downturn while competitors are forced to sell at a loss just to stay in the game. Tesla paired that cost target with two more ambitious goals: eliminating rare earth materials from its motors and slashing the amount of expensive silicon carbide used in its power electronics. Both matter for reasons that go well beyond the balance sheet. The rare earth elements used in most high-performance electric motor magnets are refined almost entirely by a small handful of suppliers concentrated in one part of the world. That concentration hands enormous leverage to whoever controls that supply chain, with the ability to move prices or availability with little warning. A motor that needs far less of that material insulates Tesla from a vulnerability the rest of the industry still carries. It's worth being clear-eyed here. As of early 2026, a fully rare earth-free Tesla drive unit hasn't shipped in volume. These remain declared engineering targets rather than delivered reality. But the direction of travel, designing scarce, geopolitically sensitive materials out of the car altogether, tells you a great deal about how Tesla thinks about long-term risk. None of this works in isolation. A cheaper, more efficient motor is only valuable if the rest of the factory around it is built to take advantage of it. And this is where Tesla's manufacturing philosophy becomes just as important as the motor itself. Tesla has leaned heavily on giant single-piece aluminum castings to replace what used to be dozens of individually stamped and welded components in a car's underbody. Fewer parts means fewer robots on the line, less floor space required, and fewer places for cost or defects to hide. The battery pack itself has been engineered to double as a structural element of the car, bearing physical load rather than simply riding along as dead weight bolted to the floor. And Tesla has pushed further upstream than almost any other automaker, moving into refining its own battery materials and even processing lithium domestically, rather than depending entirely on outside suppliers for the most expensive component in the vehicle. Every one of those choices, the casting, the structural battery, the vertical integration into raw materials, and the motor itself, is designed to work as a single connected system rather than a collection of separate departments optimizing their own piece of the car. That's the layer competitors find hardest to copy, because it isn't one clever innovation you can reverse engineer from a teardown. It's the accumulated result of building cars badly, then less badly, then well, over more than a decade, with every failure folded back into the next iteration of the factory. A rival can buy the same giant casting machine Tesla uses. What it can't buy is the decade of failed castings that taught Tesla's engineers how to actually run one profitably. The deeper you look into how Tesla is structured, the harder it becomes to describe it purely as a car manufacturer. Every vehicle on the road is also a rolling data collection device, feeding driving information back into the systems Tesla uses to train its autonomous driving software. More cars on the road generate more of that data. More data trains better software. Better software sells more cars. And more cars generate still more data. It's a feedback loop that compounds over time, and is a loop a competitor can't shortcut by simply spending more money. They would need years of vehicles already on the road, desirable enough that people actually bought them, just to begin closing the data gap. That same philosophy extends into energy storage, where Tesla builds large-scale battery systems for homes and utility grids using much of the same cell technology, power electronics, and manufacturing discipline that goes into its cars. It extends into computing, where Tesla has invested heavily in custom silicon designed specifically to train its driving software on the flood of video its fleet generates. And it extends into robotics, where the same artificial intelligence trained on years of driving data is now being applied to a humanoid robot Tesla has described as a potential long-term pillar of the business, even though that program remains early and unproven. The clearest expression of this broader ambition is Tesla's push into autonomous ride-hailing. A self-driving vehicle isn't just a one-time sale anymore. It's an asset that can theoretically generate revenue around the clock, turning a parked car into an active earner. Whether that vision arrives on the timeline Tesla has promised remains genuinely uncertain, and the company has missed self-driving deadlines before. But the underlying logic hasn't changed. The cheaper each car is to build, and the more of them there are on the road, the more valuable a working autonomy system eventually becomes. None of this means Tesla has had an easy run recently. The Cybertruck, once positioned as the company's boldest statement yet, struggled badly to meet its own sales projections and became one of the more publicly scrutinized disappointments in Tesla's history. Recalls chipped away at consumer confidence, and a wave of new, genuinely competitive electric vehicles from rival brands gave buyers options that simply didn't exist a few years earlier. For a company whose entire reputation rested on the idea that everything it touched would reshape its category, a stumble that visible mattered. But it's worth separating the fate of any single model from the underlying engineering and manufacturing advantages the company has spent over a decade building. The motor, the casting technique, the vertically integrated supply chain, and the data flywheel don't disappear because one product underperformed. If anything, a rocky year has forced sharper scrutiny of exactly where Tesla's real advantages lie, and increasingly, that advantage looks less like a specific car and more like the industrial machine quietly humming underneath all of them. It would be a mistake to suggest that rival automakers simply sat still while Tesla pulled ahead. The last several years have seen genuine, well-funded attempts to close the gap, and understanding why most of them fell short says as much about the difficulty of the problem as anything happening inside Tesla's own factories. Ford's dedicated electric vehicle unit produced vehicles that reviewers genuinely liked. The Mustang Mach-E built a loyal following, and the F-150 Lightning brought electric power to America's best-selling vehicle nameplate. But by Ford's own financial disclosures, that division lost billions of dollars a year, forcing the company to delay planned models and lean harder on hybrid technology as a bridge strategy. General Motors, despite decades of electric vehicle experience dating back further than most people realize, repeatedly pushed back the rollout targets for its next-generation battery platform as production struggled to ramp to meaningful volume. Volkswagen committed tens of billions of dollars to electrification in the years following its diesel emission scandal, only to be slowed by persistent software problems inside the in-house division responsible for tying its vehicles together digitally. Smaller, newer entrants told a similar story from a different angle. Lucid built vehicles that set records for efficiency and range, but has continued to produce them in relatively small numbers while working towards sustainable profitability. Rivian built genuine demand for its trucks and SUVs, yet for years lost money on roughly every vehicle it delivered, while fighting to bring manufacturing costs down to a workable level. These aren't stories of incompetence. They're stories of just how difficult it is to build electric vehicles that are simultaneously desirable, high-performing, and profitable at meaningful scale. The exact combination Tesla spent a painful decade learning to deliver. The one major exception is BYD, which has grown into a legitimate global rival, and by many measures, now sells more electric vehicles worldwide than Tesla does. But BYD has largely won that race by competing aggressively on price, flooding markets with lower-cost models, rather than chasing the specific combination of performance, efficiency, and premium positioning that defines Tesla's strategy. It's a different kind of competition, aimed at a different part of the market, and it doesn't directly challenge the manufacturing advantages built around Tesla's drive unit. What makes Tesla's position particularly difficult to challenge isn't any single advantage in isolation. It's the way each one reinforces the next. A cheaper motor lowers the cost of building a car. A cheaper car can be sold at a lower price without sacrificing margin. A lower price attracts more buyers. More buyers on the road generate more driving data. More data trains better software. Better software makes the car more desirable, which attracts still more buyers, which funds further investment in manufacturing efficiency, which lowers the cost of the next motor. That loop is difficult to break into from the outside, because a competitor entering late doesn't just need to match Tesla's current motor. They need to somehow replicate a decade of accumulated manufacturing experience, a battery supply chain built from raw materials up, a fleet of vehicles already generating real-world driving data, and a charging network that has become reliable enough that rival automakers have started adopting Tesla's own charging standard for their vehicles rather than competing with it. A rival might successfully match the motor and still lack the cell technology. Match the cell technology and still lack the data. Match the data and still lack a factory system efficient enough to make any of it profitable. Closing one gap doesn't finish the race. It just reveals the next gap waiting behind it. That's not to say the outcome is guaranteed. Manufacturing advantages can erode. Talented engineers move between companies, patents expire, and technology that looks impossibly difficult to replicate today can become standard practice within a decade. The same way Tesla's own charging connector went from a proprietary advantage to something rival automakers were eager to adopt. History is full of dominant companies that assumed their lead was permanent and were proven wrong. But for now, the structural advantage Tesla has built runs deeper than any single component. And that's precisely what makes it so hard for the rest of the industry to simply engineer its way around. Zoom out far enough, and the story of the carbon-sleeved rotor stops being a story about a car part at all. It becomes a story about what happens when a company refuses to accept a limitation the rest of an industry has quietly agreed to live with. Every major automaker on Earth had access to carbon fiber. Every one of them employed engineers capable of understanding the physics involved. What separated Tesla wasn't access to a secret material or a hidden formula. It was a willingness to absorb years of expensive failure in pursuit of a manufacturing process nobody else was confident enough to commit to at scale. That willingness has since spread across nearly every part of the business, from battery cells to charging infrastructure to the software running inside the car's onboard computer. And it's why an increasing number of analysts describe Tesla less as a car company that happens to build good technology, and more as a technology company that happens to sell cars as its most visible product. Strip away the marketing and the headlines, and what's left is a fairly simple story about a manufacturing decision most of the industry didn't think was worth making. Tesla looked at a physical limitation everyone else had accepted as permanent, decided it wasn't actually permanent, and then spent the better part of a decade absorbing the painful, expensive lessons required to build that solution reliably and cheaply at enormous scale. The carbon sleeve rotor was never really the finish line. It was proof that the assumptions the rest of the industry had built their strategies around might simply be wrong. Whether any competitor manages to close that gap in the coming years, through their own engineering breakthroughs, through partnerships, or simply through sheer scale, is genuinely an open question, and reasonable people disagree about the answer. What's harder to argue with is that the terms of the competition have shifted. This is no longer just a race to build an appealing electric car. It's a race across motors, batteries, software, data, and manufacturing all at once. And right now, only one company is positioned to compete on every one of those fronts simultaneously. So the real question isn't whether Tesla built an impressive motor. It's whether the rest of the industry can rebuild an entire decade of manufacturing experience fast enough to matter, before the target moves again.